Hi, Jamie.
Hi.
How you doing? Jamie wants to get up close here.
I do. What's better than being up close and personal with calc? Or send away from me. Same as sitting on the edge of the seat. You want me to do that way? Yes, please. Give AB a nice huge bump.
I don't know why it doesn't follow me sometimes. Okay. All right. The properties of integrals that we talked about yesterday, we wrote down like 4 or 5 of different ones. Okay, we have those. One of them said that if you take the integral from 0 to 6 of a function, and that we have a number that's in between the 0 and the 6, we can break up the integral into the sum of 2 other integrals. Okay? These 2 things then are added together by computing what the integral means to finally get to the answer. Okay? Now, just want to summarize a little bit about what we've been doing. We've talked now for like 2 weeks about this thing called the fundamental theorem of calculus, and then how it has to do with the net change, or what we're also referring to as displacement. Okay? We've learned that areas that are above the x-axis, for example, can demonstrate on a particle motion problem that that's where the function is moving to the right. Okay? Areas that are bounded by the derivative below the x-axis can demonstrate that's where the function is moving to the left. The actual area above or below tells the actual amount that the particle is moving. Okay? This should all sound familiar. Okay? But then we said, wait a second, there's this crazy thing. This integral that we talk about here, not only can it compute the amount of change in something, like we did the snow, remember we did like snow, and we did like the cost of a bottle of wine, remember that one? Or the puck traveling. There's like an infinite number of ways that you can apply the fact that this integral symbol, which it's actually this big S, stands for sum, because it can accumulate the amount of change in whatever function that you give it. So it has that ability. But I don't know if you or your mom or your dad have ever been in a situation where like you're doing some kind of project and you got a screwdriver and you're like tightening a screw or something like that, and then at the same time then you need to like nail in a nail, and you're like, well, I don't have my nail around, or I don't have a hammer around, so I'm just going to use my screwdriver, dung, 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 dung. And it doesn't work as well, but it can work, right? In other words, the screwdriver had multiple purposes that were completely different from each other. One was to tighten a screw, and the other one was to hammer in a nail, right? Multiple purposes. Well, it turns out this integral has also multiple purposes. One of it is the most important thing is that it does this whole net change thing, which is amazing. The other thing is that kind of out of the blue, it allows us to calculate areas of odd shapes that are not geometric. Okay? It can do both of those things. They're somewhat related, but they're kind of also not related. Because you could do an area problem, and the area problem doesn't have anything to do with anything changing. We just want to find the area. Okay? So it has these 2 different purposes, and all of the rules still apply. All right, so this was the one where we have it in between. This is another one. If you go from 6 to 3, then the answer is the opposite of going 3 to 6. It's changing the interval. The other one is if you have a constant multiplied by the function inside the integral, you can pull out the constant and multiply it by the result of the integral. These are all different applications of the properties that will help us to figure out what any of these integrals are. The most important thing that I want you to realize is that the answer to a definite integral is some number. Okay? It can be positive, it can be negative, it can be 0. If we're trying to do an area problem, and we just want to know what the area is, and we do an integral that maybe looks like, we say, I got this weird function, I don't know what it looks like, but I want to know what's the area of all that. But I do have this function, it's defined by f of x. Well, I can go from this value to this value. I can write the integral from a to b of f of x dx. What kind of answer is it going to give me? It's going to give me a negative answer. But if I only care about whether or not what is the area, then I just say, okay, but I'm just going to take the positive. Great question. For example, if we have a circle right here, okay, can we find the area here using a single integral? That's what you're asking, right? And the answer is no, not directly. Okay? If you stop and think about this, I want you to keep thinking about this because we're going to actually do this. But I want you to think about how the heck do you find the area of a region that's bound by not a function but a relation.
So would that be the same for a hexagon? Like an 8th grader asked you how to find the area of a hexagon?
If an 8th grader just hypothetically asked me to find the area of a rectangle or of a hexagon, yes.
We were asked that last night.
Oh.
Kayla and I were.
Do you know the area of a hexagon?
We said divide it up into triangles. Divide and conquer.
Perfect. Exactly. It's a good call.
Good call.
Yeah.
Give them their ass one and a half, multiply by 2, and then have
Not the word. Not the word.
Sure. Top half. And then multiply it by 2? Yes. The only problem is then we got a problem. We don't have that. These are chatty today. All right. Homework is due 278 is due on Monday. I was nice to you. Okay. And today we're going to take a look at Riemann Sum. So take out your notebook and copy that down. Everybody's kind of chatty today. It's from everybody pulled all-nighters because scholarships are due. You had what?
Oh my gosh.
talking retirement funds?
Yeah.
Okay, good. It's a good idea.
You gotta start early these days.
Because I heard the rumor you might be retired in a few years, and then it brought up Mr. Rumpke, and then that was a false alarm.
False alarm. Today is the 29th. Okay. That's my Desmos login. All right, pull out your calculator and get an answer.
It's true.
Yeah. If I dye my hair. Okay. This is not the first time this has been asked, okay? All right. Let me give you the scoop on the hair. Okay? Here's the scoop on the hair. I do not dye my hair. Now, it may be a common belief out there, legend, that I dye my hair, but it's false. Okay? Here's the deal. My family has a gene which is a freak hair gene. Okay? It's like mutant. Okay? And here's the deal. When I was younger, my hair was probably closer to Jonah's over here. Okay, that used to be the color of my hair. Okay? Yeah. And the thing about the Johnson hair gene, the Johnson mutant hair gene, is that the older you get, the darker your hair gets. So, my mom is 81 years old. She still has black hair. Yeah. She's got a little sprinkling. She only recently started to get a few gray hairs. But I have not a single gray hair on my head.
We need proof. Or you just think it's
Yeah. That's right. That's right. That wouldn't be the case, though.
Did you like just when you were a child, just a ton of black hair dye? And just
Well,
so it emptied?
my wife hates me for it. Okay, but she says, now be careful what you ask for because this could become a problem as you get older. Okay, does anybody know of a guy, an entertainer in Las Vegas by the name of Wayne Newton? Okay, if you Google Wayne Newton, I don't know, he's like 200 years old. But he still has this jet black hair because he dyes his hair, okay? And there comes a certain moment in a person's age where all of a sudden black hair just kind of starts to look freaky. And she says, you're going to cross over to that. And then now what? So that's what I asked the lady who cuts my hair. I said,
Yeah, no, never mind, I recognize.
"You recognize that guy?" Okay, there's Wade Newton. She says that's what you're going to look like. Yeah. I think it's part of the freakish look. Well, here's the problem. So I said, "Oh, this is easy. Easy solve. I'll just buy colored dye that puts gray in my hair." Right? But it turns out that because of the pigments and all that, you cannot dye black hair into it. So, oh yeah, that'll turn out good. Oh God.
Yes.
If we all pass the AP test.
Yes.
If we all pass, everyone pass the AP test, that would be bad.
I am not going to commit to anything, but I'm tempted by that. If we got 100%, then I will strongly consider it.
What if your wife approves it?
Yeah, she won't approve it.
Well, what about a wig?
Well, all right, so that's the story on the hair. Okay? Oh, by the way, my two sisters, one sister's 2 years older, the other one's 4 years older, and they both have black hair too. They both have the gene. They got a little sprinkling of gray, and actually my grandpa died. This my mom's dad died when he was 78, all black hair. So it's a genetic mutation.
10 minutes later.
Yeah, I see what you're doing here. All right, what'd you get for an answer? 1.3 repeating, right? Same as 4/3, same as 1 1/3, and so on. Okay? Now, we can accept that as the truth, that this is what the answer is, because the calculator would never lie, right? And so, look back over here. This picture, okay, this picture represents the area, and obviously in geometry class, when you were doing areas of different figures, you were never asked to compute the area of a figure like this because it had this curve, and they said, no, we're not going to do that because we can't. Okay? Because it's not a polygon, it's got this curve to it. So this poses a problem. Okay? So the calculator computes it in some way. The question is, how does it do it? How does it compute that area? And so that's what we're going to take a look at today. And the answer is, it does it with these things called Riemann sums. Now, Bernard Riemann was a mathematician. We were friends on Facebook. Then he said a couple of things I didn't like, so then I unfriended him. So the answer is, so the question is, how does it know? Okay, how does it know the answer? And the answer is, it does what are called Riemann sums. Okay, and what we're going to learn today, and what you have to actually know on the AP exam, is what a Riemann sum is, and then how to compute them. Yeah, right there. Okay, so let's take a peek at what a Riemann sum is. So back and forth here.
There's people who haven't signed the Swivl waiver.
Who?
Mary Wilson and the girl who was just in here.
Oh, yeah. Mary Wilson. We got to give you the waiver. Okay? Or you could just put the lunchbox over your head. Okay, so take a look at this. Let me tell you what a Riemann sum is. So I have the function y equals x squared plus 1. I have the same exact function here. Okay, and what we're going to try to do, and I've exploded it so it's just the region that we want. So the first thing I'm going to do is, since we're out to just to find an estimate for it, okay, is that a good estimate? First of all, is that rectangle an estimate of what the actual area is? Yes. Is it a good estimate? No. Okay. So in fact, the area of this is 1. Look at the estimated area. That's what this is. And then the actual area is the 1.3 repeating. Okay. So if I don't use 2 rectangles, if I don't use 1, I use 2, is this a better estimate? Yeah, actually it is. Our goal is to fill this whole thing. 3. That's closer. 4. Oh, let's do 10. Look at how close we are now. This estimated answer. Now we know how to compute the area of a rectangle. That's easy. Here we just compute 8 different rectangles, add them up, and we get our answer. 22. So now we got 1 decimal place accuracy. It's 1.3. 100. Ooh.
It's not close. Not in the real one. 1,000. Rounding is. Maybe I can't do 1,000.
No, I know I can. Because I tested it. That's pretty good. Well, wait a second. How many rectangles would it take?
An infinite amount.
An infinite number. Okay, now stop and think about that. We can subdivide this, and if we had a really large number, like 1,000 of them, we get still pretty close. Here's 2 decimal places, almost 3 decimal places of accuracy. But to get the actual one, we would actually need an infinite number. Okay, now wait a second. We can't actually do an infinite number, right? But if we had if we had some sort of limit, because that, limits allow us to get close to something. We could have it approach, if we could somehow find out what the answer is, if the number of rectangles approaches infinity, because we can't actually get there, then we could probably figure out what the answer is to that. Sound good? I wonder how we're going to do that. Well, let me show you. This right here is what's called a left-hand Riemann sum. Okay, left-hand Riemann sum. And the reason why it's called that is because the functional value, take a look right here. The functional value of the rectangle uses the left side to determine the height of the rectangle. Okay? Every rectangle, the left side touches the function. Okay, it's a left-hand Riemann sum. Now there's a different one. Here's a right-hand Riemann sum. And the reason why it's called a right hand is because the right side of the rectangle uses the height of the rectangle is based upon the functional value. If you took those two and added them up and divided by 2, you're going to get an answer close to the midpoint Riemann sum, which is actually, you can get far more accuracy by doing the midpoint. Okay, look at, we already got 2 decimal places of accuracy doing a midpoint. Okay, back to this. Notice that my function is increasing. Okay? If I plot this, is my estimate for the answer an overestimate or an underestimate of the real answer? It's an underestimate because the function is increasing. Okay? Right hand, this is an overestimate. Okay? Now, if I change the function around so that it's decreasing, okay, this is a decreasing function. Is this a, when you look at this picture, can you tell if it's that it's a right hand? And the reason why you can tell it's right hand is because the right side of the rectangle is what's touching the function. Here, this is a right hand, but is it an overestimate? No, it's an underestimate. So it matters whether or not the function is increasing or decreasing to determine if you have an overestimate or an underestimate of the real answer. Okay? And you can put in any kind of function that you want to, and it'll do it. Okay? And I'm going to go, let's do unable. I guess you can't do everything. Can you do a square root? I didn't even try this. I guess not. Okay, so if I just simply have a linear function, this is the only one, a linear function, that if I do a midpoint, the actual answer is equal to the estimate. Because what happens here is, if you were to just picture this for each one, if I snip off this part of the triangle right here, it fits perfectly into this one when the function's linear. But as soon as you make this a curve, the snipping doesn't work. Make sense? Okay, so what we're going to do is we're going to do left hand, right hand, and midpoint Riemann sums. And we're going to demonstrate how to compute this. And we're going to try to get exactly what the answers are for each one of these. And we're going to make it simple. We're just going to do 4. Okay? So, and this is how, go back to why we're doing this. How does the calculator do it? It uses Riemann sums to calculate the answer here. And some of you might say, well, why do we need to know it if the calculator is going to do it for us anyway? Okay? Here's the difference between you and everybody else. You guys are going to be the ones responsible in the future for developing the new things that are needed for the improvements in our world. Okay? Our lives are in your hands.
No pressure or anything.
Right? So, for example, if you're a programmer, okay, think about this. This is actually a simple loop with a calculation of multiple rectangles. And you're accumulating the sum, and you get the answer. That's what's buried inside that calculator, is a piece of just a little snippet of code that goes through a loop that accumulates the area of each of the rectangles. See, so software developers have to know how the math works to be able to provide things, good things for the general public. Okay, that's how this works. But if you stop and think about it, if we didn't teach this, then we would never advance as a society, because we would just be stuck with just knowing the things that we know. And your job is to learn more so you can make life better. You know what I'm saying? So that's why I teach you where things come from, why we're doing it, so that it makes sense. And you got to remember that in your lifetime, you're going to ask to do a lot of things that have never been done before. And you have to be able to think rather than just being able to duplicate what your teacher does. Okay, so let's do this one. So we can get started. Let's do a left hand. Let's simulate this one right here and get that answer. So, yes? Would it be what? They can actually stick it in either one based upon how they state the question. Okay, so let's go do this. So we're going to find this answer manually. So here is the question. So we're going to do 3 problems in one. Okay. Given f of x is equal to x squared plus 1 on the interval from 0 to 1, find the 3 Riemann sums, and that is the left, the right, and the midpoint, okay, using 4 rectangles. In your homework, you're going to have to do this exact same thing. Okay, so now we're going to draw the function. So let's do the left one first. So this is the left-hand Riemann sum. So what I want you to do is I want you to draw the function, but kind of exaggerate it. Okay? So if you'll notice, I've exaggerated this to the point where I can easily draw the rectangle. So the function goes from here to here, and it's this curve. We're simulating that right there, and we're going to find the area. So this is my function. F of x is equal to x squared plus 1. My goal, estimate the area of this using a left-hand Riemann sum. And with n equals 4. Okay. N equals 4 means that's the number of rectangles. Okay. All right, so let's divvy this thing up. So since we have 4 rectangles, we want to split this up into 4 pieces. Okay. And they're 4 equally spaced. And go ahead and draw the vertical lines that are going to be the left and the right sides of the rectangle. Okay. Now we need to put the tops on the rectangles. So for each one of these, we're using the left side of the rectangle to compute the height of the rectangle. This is the left-hand Riemann sum. Okay. All right, so let's go label all where these are. So what are these markings? Mm-hmm. 2.5, then a 3/4, and then a 1. Okay. All right, what I'm going to do is I'm going to label these A with a subscript of 1, 2, 3, and 4. That way, I can say this. I can say that my estimated area, which is my area as a left-hand Riemann sum, so A with a subscript of L for left is equal to A sub 1 plus A sub 2 plus A sub 3 plus A sub 4. Okay. Remember that this is the estimated area, or if I just put A, that means it's the actual area. Now, if you're in stats, you might see this. Okay. Can everybody read that? This is that big symbol right there. That's the sigma. It's the Greek letter sigma, which stands for sum. Okay. So it's summation. This is actually what's called summation notation. And what happens here, it's a for loop, if you know computer science. It's a for loop where n goes from 1 to 4, and the n is replaced by that value. So this is equal to A sub 1 plus A sub 2 plus A sub 3 plus A sub 4. Okay, so that's the notation there. So the book uses this notation, this sigma notation, a lot, and so you'll come across that in your reading. Okay, well, let's keep going here. Oh, by the way, what's this? This is A sub fables. Childhood books, fables, Aesop's fables. All right. I tried. All right, so we're going to do this very mechanically. The area of each one of these rectangles is length times width. So let's go figure out what each of those are. What's the length? Just a matter of what we decide is length and width. So let's call this width, and we'll call this length. Okay? So I need to know what each of these are. So we just plug them into the function, right? So what's the first one? 1. So this becomes 1 for a length, and what's my width? 1/4. Okay, next one. 1 1/4. Okay. 1 1/4 times, what's the width of that one? Notice that the width is still the same. They're all the same widths. Okay, what's the next one? I'm just taking your answers, so. Is 1 1/4 correct? No. Okay. Something's only true if you believe it to be true, if you don't say anything. So 1/4 squared plus 1, this is 1 1/16, is it not? Okay. So this is 1 1/16. Okay, what's the next one? That one's 1 1/4. Width is 1/4. What's the last one? All right, we'll fill up this one, and then that's going to do it for today. Does everybody agree that this is 3/4 squared plus 1? 3/4 squared is 9/16 plus 1. So the answer is 1 and 9/16. Times a quarter. All right, we'll finish this on Monday. Get your homework done by Monday, because you're going to get a new one on Monday.